Hello, good evening. Welcome to the last tutorial session of uh, power electronics applications in power systems. This is the 12th week. I shall share my screen now. I hope the screen is visible. Okay, so let's start today's session. In the last week, we started to discuss about the converter-based compensators. So in the earlier sessions, the uh, the compensators that were discussed were not converter based. So they were basically like we talked about HVC, static var compensator. Then we talked about different types of HVC. Then we talked about the series compensators which would so the shunt type compensators would offer variable susceptance to compensate the reactive power, and the series type of compensators would offer variable impedance to the network so that the reactive power compensation can happen, right? Now uh, now the difference with these type of compensators with the converter based compensators is that here power electronic converters are used and they are modulated to inject some amount of reactive power as per requirement or absorb some amount of reactive power, right? So here uh, power electronic converters are used. Okay, so there is so that variable susceptance of variable impedance, that concept is not there. Okay, so the first power electronic based compensator that was discussed was STATCOM. The full form is static synchronous compensator, and today we will discuss about static synchronous series compensator, which is the short form is SSSC, SSSC. Okay, static synchronous series compensator. So obviously from the name you can understand that this is a series compensator. Statcom was a shunt compensator, but this is a series compensator, right? Now, yeah, so we will discuss about its various applications, just like Statcom, and also we will discuss the different control modes of SSSC. So this table in the last session also we showed that these are the types of power electronic based compensators, shunt compensator and series compensator, and SSSC comes under series compensator. Okay, here. And obviously there were power transmission converters for used for power transmission systems and converter based compensators used for power distribution systems. SSSC is used for power transmission systems. So STATCOM and SSSC both are used in power transmission systems. Okay. Now let's see what does a triple SC look like. This is the this is a simplified diagram for a triple SC. So there is this step down transformer, and then there is triple SC, which is nothing but a voltage source converter. Okay, VSC. VSC is a voltage source converter, right? And here there is the DC link, this capacitor. Okay. So usually if you see a structure of a VSC, normal VSC, there will be an active source. There will be an active source, DC source. Then there is some, and obviously there will be some internal resistance associated with this DC source. And then there will be DC link capacitor, and then there will be VSC. Okay, which there will be three half bridges usually for a three-phase system like this. These are basically semiconductor devices. Okay, you will have to choose proper semiconductor devices. You can use IGBT or MOSFET. Okay, or thyristor, something like this. And then output will come out like this. Output will come out like this. So here you will get the three-phase output A, B, C, right? Here if you see, for triple SC, there is no active source. There is no battery or DC source connected with the triple SC. Why? Because uh, triple SC is essentially used for reactive power compensation. If we connect a DC source over here, then we can also do active power exchange. But for now, we will assume that only reactive power exchange happens. That's why there is no active source connected with the triple SC. Okay. So no active power exchange. And also another assumption is this unit is lossless. This assumption we have taken for other compensators also, that they are lossless. Okay. And obviously a symmetrical lossless three-phase transmission line. Okay. So this we understand that this is a three-phase voltage source converter, and the step-down transformer is used to reduce the rating. Step-down transformer, and then there is a circuit breaker in parallel. What is the use of the circuit breaker? In fault in there, suppose there is a fault in the transmission line, and we need to protect the triple SC. In that case, what we can do is we can close this circuit breaker. And what will happen if we close it, then it will bypass this whole thing. When the circuit breaker closes, it is bypassing because it is providing a alternate path for the current. So this triple SC is getting bypassed. That's how it can protect the triple SC in faulty condition. Okay, so let's proceed to the next part. Yeah, now if you just represent it in like in a single line diagram, Suppose this is the sending end, this is the receiving end. The sending end voltage is V angle delta and the receiving end voltage is V angle 0. And this is the representation of the triple SC like a variable voltage source like this in series with the line. And this is the line reactance Jx, and the current is flowing like this from sending end towards receiving end. And just apply KVL here. V delta minus Vs minus Jix is equal to V angle 0. What is Vs? Vs is the voltage of the triple SC. And what we get, V delta minus V0 is Vs plus Jix, right? This is what we get. And now, in terms of phasors, we can represent them. This is V angle 0, the receiving end voltage, and there is a delta phase angle difference of delta between sending end and the receiving end voltage. This is the sending end voltage, and this whole angle is delta from here to here, from here to here. Okay. Now, V angle delta minus V angle 0. So this quantity, what is this? This is equal to Vs plus Jix, right? So that's why this red one, this red arrow, red phasor, this represents Vs plus Ix. Okay. Why plus minus Vs is used? Because the the triple SC can inject either positive voltage or negative voltage. That's why this plus minus. Okay. So this is the phasor. Now, obviously, as it is used for reactive power compensation, two cases may arise. The first one is the current, the line current basically. Either it will lead this voltage Vs by 90 degree or it lags this voltage by 90 degree. So case one is I lags Vs by 90 degree, right? And the second case is I leads Vs by 90 degree. But either way, there will always be a 90 degree phase difference. Whether it is the lagging or leading, the current is lagging or leading, the phase difference is 90 degree because it is reactive power compensation. There is no active component, right? So that's why it is 90 degree always. Now when I lags Vs by 90 degree, then obviously this is inductive mode of operation, and when I leads Vs by 90 degree, that is capacitive mode of operation, right? These angles from I to V, this one and this one, they are delta by 2, right? So this Is plus minus Vs is equal to 2V sine delta by 2, right? Because this angle is 90 degree and this angle is also 90 degree. So so this part, this from here to here and from here to here, they are equal, right? They are equal. So this is equal to 2V sine delta by 2. And now after some simplification, what we get, I is equal to this 2V by x sine delta by 2 plus minus Vs by x. So there this Vs term is involved. Okay. And you can understand that this current I, this current linearly varies with this voltage, right? For a particular operating condition, suppose V is constant, and at a particular operating point, this there is a particular delta power angle. So if this quantity is constant, then the current changes with Vs linearly. Okay. And that is proved from this equation. Now, if we just compute the power, the active power, what is the active power? Vi cos delta by 2, because the phase difference of the line current and the voltage is delta by 2. Now, replace the substitute I with the expression that we just got, with this expression. If you just substitute it, you will get an expression like this, right? Like this, and finally P comp is this. So this part you are familiar with. This part you are familiar with. This is the power when there is no compensation. V square by x sine delta. This is usually the active power, the power flow in the transmission line. The extra term, this one arises due to the compensator. VVS by x cos delta by 2. So even when delta is equal to 0, when power angle is equal to 0, P comp is not 0. You can see, because cos delta by 2 is non-zero. That's why if you see this red curve, there is some, even at delta equal to 0, there is some P, right? That occurs due to this extra term. Fine. So when Vs is equal to Vs is positive, then you get a positive power. But if Vs is equal to Vs is negative, then this power is negative, right? This power is negative. And what does the negative power signify? Negative power means the power is basically, usually power flows how? From sending end towards receiving end, right? From sending end towards receiving end. But in this case, the power will flow from receiving end towards sending end. Therefore, from the power equation, we can conclude that if Vs is negative, then the power flow is reversed. The direction of power changes. Okay. So this is an important point for SSSC, that power reversal can occur. Okay. Okay. So now let's start the questions. The first question is, which of the following component is essential for the operation of SSSC? Circuit breaker, interfacing step down transformer, thyristor switched capacitor, or voltage source inverter. So circuit breaker is a, we use circuit breaker for in the SSSC circuit we saw there was a circuit breaker, but this is a protective element. Circuit breaker is used to protect SSSC when there is a fault condition. Second is interfacing step down transformer. This is used to reduce the rating. Thyristor switched capacitor, this is not used at all. There is no thyristor switched capacitor in the SSSC circuit. And voltage source inverter. This is the most important element, because SSSC is nothing but a voltage source converter, I told you. So this is essential for the operation of SSSC. Without this, uh, SSSC cannot work, because the SSSC circuit is nothing but a voltage source converter. Okay, these things are important, but without this also SSSC can work. But this is absolutely necessary. So option D, voltage source inverter is the correct option. Next, which of the following is not a component of SSSC? So circuit breaker is present. So this is a component. Interfacing step down transformer is also required. Thyristor switched capacitor voltage. So the same options. This is not required. This is not a component of SSSC. Okay. Next, SSSC can be represented as. How we can represent SSSC in terms of electrical equivalent component. Whether it is a variable shunt current source, a variable series current source, a combination of shunt current source and series voltage source, or a variable series voltage source. So obviously this is a series compensator, and we just saw when we were discussing the single line diagram that there we represented it as a voltage source in series, right? In series with the line. In series with the line like this. Okay, and this is variable. So option D is correct, a variable series voltage source. Next, which of the following is the correct statement? SSSC injects voltage in series only when there is an active power exchange between the SSSC and the network. This is not true because SSSC is mainly used for reactive power compensation, and even if there is no active power exchange, it will definitely inject some voltage for reactive power compensation. So this is not correct. SSSC can inject variable current in shunt, thus can be represented by a variable shunt current source. This is also not correct. We just saw that SSSC is represented by a series voltage source. A circuit breaker is connected to enhance the operational capability of the SSSC under heavy loading condition. Circuit breaker is not used to enhance the operational capability. Circuit breaker is used to protect, to bypass the SSSC when there is fault in the line. This is also not correct. So this is not correct. This is not correct. And this is also not correct. The last one. In voltage control mode of SSSC, the injected voltage is independent of the line current. What is voltage control mode of SSSC? That we will have to understand. What is voltage control mode? So if you remember for STATCOM also, we saw the control characteristic of STATCOM. So here also there are two control modes. Okay. So there is voltage control mode and there is reactance control mode. So reactance control mode is there for SSSC. Okay. What is voltage control mode? So the voltage is maintained constant irrespective of the line current. Okay. That is the voltage control mode. This is the control range. Okay. From here to here. From here to here, this is the control range. You see that the voltage remains constant. Although the current is increasing, line current is increasing, but the voltage of the SSSC remains constant. Okay. So yeah, so this is the positive voltage and this is the negative voltage. Okay. But irrespective of the current, the voltage is constant. That's why this is the voltage control mode. And in reactance control mode, you see there is a linear relation between the voltage and the current. Okay. Because here the reactance is being controlled. Okay, the reactance is being controlled. And obviously the slope is constant here because we are controlling the reactance. So this is the capacitive, this positive voltage is the capacitive mode when positive voltage is getting injected, and this is the inductive mode when negative voltage is getting injected. Okay. So these are the two control modes of SSSC. Okay, next question. What is the effect of capacitive operation of SSSC on the power flow through the transmission line? So what is the effect of capacitive operation? It increases the power flow, it decreases the power flow, it has no effect on the power flow, it decreases the power loss and does not affect the power flow. Okay. So if we just refer to the power flow equation, so this was the equation we finally got, and this was the extra term. In capacitive mode of operation, Vs is greater than 0, right? Vs is greater than 0. So obviously you can understand that the power is more, if the line was uncompensated, this was the power. So if Vs is positive, the power flow increases, right? Because this term is added to the usual term. That's why it increases the power flow. Option A is correct. Question number 6. In reactance mode, control of SSSC, the impedance is kept constant at maximum value. Okay. Then what is the true? Which of the options are correct? The injected voltage is independent of SSSC current. The SSSC voltage varies inversely with the SSSC current. The SSSC voltage varies linearly or inversely in the inductive or capacitive mode of operation, respectively. The SSSC voltage varies linearly with the SSSC current. Now we saw the two different modes of control. One was voltage control mode, another was reactance control mode, right? So if we just refer to the two control modes, in voltage control mode, we saw that the voltage was remaining constant irrespective of the line current. The line current may increase from here to here, but the voltage is remaining constant. But here, but in reactance mode of control, there is a linear operation. So the voltage and current, the relationship is linear, right? So the current, the voltage increases linearly along with the line current. Okay. So the SSSC voltage varies linearly with the current. This is the correct option. Question number 7. Which of the following is not an application of SSSC? First is damping power system oscillation, injecting reactive power, filtering harmonics, and damping subsynchronous harmonics. So SSSC can damp power system oscillation. That is an application. Obviously, injecting reactive power, this is an application. This is the main purpose of employing the SSSC. Filtering harmonics, then damping subsynchronous harmonics. Now, SSSC is immune of subsynchronous harmonics, which is also called, the acronym is SSR. Okay, SSR, subsynchronous resonance. Okay, SSR SSR is short for subsynchronous resonance. What is subsynchronous resonance? So earlier in the reactive power compensators, where there was, suppose we studied about this kind of compensators, right? Where the equivalent circuit was like this. Suppose this is the line and like this, and there is a variable reactor. Okay, there is a variable reactor. Suppose TCSC or some other where there is a series capacitor. Okay. Now what may happen is there are certain inductive impedance in the network, right? Those inductive impedance and this capacitor, series capacitor, they may interact with each other and there may be a resonance, that is subsynchronous resonance. That means the resonance frequency is less than the synchronous frequency, that is the line frequency. That is called subsynchronous resonance, and that is detrimental for the system. Now, the advantage of SSSC is that there is no series capacitive element. Yeah. So the advantage of SSSC is that there is no series element, series capacitor element, right? The SSSC is a voltage source inverter. So that's why the subsynchronous there cannot be any subsynchronous resonance, right? So, and it can also damp the subsynchronous resonance by some methods, that is not that is out of the scope, but this is a advantage of SSSC, that it can damp such subsynchronous harmonics and it is immune to subsynchronous resonance. That's why filtering harmonics, this is not an application of SSSC. Other than that, these three are the applications. Which of the following is not true about SSSC? SSSC is immune to subsynchronous resonance. That is true. We just told. SSSC is capable of providing both active and reactive power to the system. This we will discuss. How? SSSC is essentially a voltage source converter. SSSC causes power angle oscillation. So this is not true. SSSC does not cause power angle oscillation. It damps power angle oscillation. Okay. So and how and these three are uh, these three are true. Okay, A, B, and C, they are true. Now when we were discussing the SSSC equivalent circuit, there was an assumption there is no active power exchange, only reactive power compensation is happening, right? But if you just add one active source here, then active power exchange is also possible. But there has to be an active source here, active DC source. Then active power exchange is also possible. So SSSC is capable of providing both active and reactive power. This is true. Okay. Next question. The power reversal in transmission line can occur due to the SSSC. Under. So power reversal, I discussed that in the P delta curve for SSSC. We saw one of the curves like this and another one like this. Okay, another one like this. right? So this is something we never encountered for the other compensators, right? This phenomena of negative power. So yeah, so this one. So I already discussed that triple SC can provide positive as well as negative power. Negative power means power reversal. The power flow direction changes. And how does that happen? When the voltage injected by triple SC is negative. Here, when delta is equal to 0, then this term vanishes because sine delta is equal to 0 and this term remains. If Vs is negative, this power flow is also negative, right? This power flow is also negative. Till this point, it is negative, and from here, it becomes positive. So the conclusion is if triple SC voltage is negative, then there is a possibility of power reversal. Okay. And when does that happen? During inductive operation, when the injected voltage is negative. Okay. Okay, so I shall take a break of 10 minutes and then I shall discuss the rest of the questions. Let's see the next question. Which of the following is true about subsynchronous resonance in transmission line? So I told you that subsynchronous resonance is the resonance that occurs between any series capacitive element and the reactive impedance present in the network transmission line. Okay, and the resonance, the frequency is subsynchronous, that is less than the synchronous frequency of the system. So SSR occurs when SSSC injects positive voltage. SSR occurs when SSSC injects negative voltage. SSR occurs when series capacitor interacts with inductive reactance in the network at subsynchronous frequencies. SSR occurs due to the interfacing step-down transformer interacting with the transmission line capacitance. Option C is correct. It occurs due to when the series capacitor interacts with inductive reactance in the network. Next question. What is the primary reason to employ phase lock loop in an SSSC control system? So, phase locked loop PLL is a circuit that is used to when when we need to interface with the grid, we need to synchronize with the grid. So this basically PLL basically gives output the phase angle. Okay, phase angle of the voltage. So it gives us theta, and with the help of PLL we can synchronize with the grid. Okay, that is the function of PLL. So the correct option is to synchronize the SSSC with the grid. I hope you know about PLL. So you can always see the block diagram of a PLL where there is a phase detection block. Okay. So suppose these are the inputs. Okay. So theta in. There are various elements like phase detection. Phase detection. I am writing PD. Then there is low pass filter. Low pass filter. Then there is also a oscillator circuit. Finally, we get the output as theta g. Okay, theta g. That is the phase angle. Okay, but obviously there is some feedback. Some feedback is required. Okay, so this is a closed loop circuit. And this is the control diagram. This is the VDC reference. Then there is the controller. Two quadrature voltages, this VD and VQ, the direct axis and quadrature axis voltages are generated. Then magnitude and phase angle calculation. This is the magnitude, this is the phase angle. Here comes the contribution of PLL. Then the gate pulses are generated and given to the VSC. Okay. The pulses are given to the VSC. This is the control diagram, closed loop control. The next question. What is the impact of SSSC in damping power system oscillation? It reduces the damping of power system oscillation. It increases the damping of power system oscillation. It has no impact on power system oscillation. It can increase or decrease the oscillation based on the control. So one of the applications of SSSC is to provide damping to power system oscillations. Okay. So del delta by del T. So basically del A. It senses the change in frequency and then proper corrective actions are taken to damp the oscillation. Okay. So it increases the damping of power system oscillation. So what is the primary function of DC link capacitor in SSSC? So if you remember the circuit, first there was the step down transformer. Here comes the SSSC, which is the voltage source converter, then the capacitor. What is the purpose of this capacitor, DC link capacitor? To balance the reactive power, to provide stable DC voltage, to filter harmonics, or to provide capacitive reactance to the transmission line. So the role of this capacitor is to provide a stable DC voltage. Okay. Next question. Active power exchange with SSSC is possible if. So we already discussed that the main purpose of SSSC is to provide reactive power compensation. And to provide reactive power compensation, there is no requirement of any active DC source over here. Without any active DC source, it can only exchange reactive power. Either it can provide reactive power or it can absorb, right? So there will be exchange of reactive power only. There will be no exchange of active power as there is no active source here. But if you just add here a active DC source, an active DC source, suppose a battery or some other active DC source, then you can also you can there is then you can also exchange active power with the transmission line with the system. Okay. So an active source such as a battery is connected to the DC link of SSSC. This is the correct option. Fine. Which of the following is not an advantage of SSSC? So the first option is the SSSC does not need bulky capacitor or reactors. The SSSC does not require power electronic converter for reactive power compensation. SSSC can provide both active and reactive power to the system. SSSC can provide damping to subsynchronous resonance. This is true. There is no requirement of a bulky capacitor or reactor unlike TCSC. We discussed TCSC, right? Whose equivalent circuit was something like this. A fixed capacitor. So this is the transmission line and a variable reactor like this. How this variable reactance is obtained? Because there will be an inductor and then there will be a thyristor circuit like this. Okay, that's how the variable reactance was obtained. If you remember the circuit was like this, right? So you require one inductor also and capacitor also. But here only a power electronic voltage source converter is required. Bulky capacitor or reactor, that is not required. Okay. Although a DC link capacitor is required to maintain the stable DC voltage, but for reactive power compensation, there is no direct requirement of any capacitor or inductor. SSSC does not require power electronic converter, but this is false because we need a power electronic converter, right? SSSC can provide both active and reactive power, that is true. SSSC can provide damping to the subsynchronous resonance, that is also true. So option B is correct. This is not an advantage because we require a power electronic converter, and SSSC is definitely a converter which is based on power electronic. SSSC is a compensator that is based on power electronic converters. STATCOM and SSSC, these two are power electronic based compensators. So option B is correct. So I think I have covered all the questions. If you have any question, you can ask. So if we just summarize the SSSC, this compensator, so we learned a few things. That is, first of all, we can, so SSSC is capable of exchanging both reactive and active power with the system. The only thing is that for active power exchange, there must be a active DC, there must be an active DC source present in the circuit. And if there is no active source in the circuit, in that case, only reactive power exchange will occur. And another important point is the active power may get reversed. That is one important point that we didn't see for any other compensator. Here we can get negative active power. And that is possible because the that SSSC can provide both negative and positive voltage. So if the voltage is negative, then the power reversal can happen. Here, this is the portion where the power flow is reversed. This is very important. Okay. Another thing is it can provide damping to the power system oscillation. It can also provide damping to subsynchronous resonance. It is immune to subsynchronous resonance because it doesn't have any series capacitive element. That's why it doesn't get affected by subsynchronous resonance. There is no occurrence of subsynchronous resonance or SSR in short. Okay. That is another point. and it has two different control characteristics. One is voltage control mode, another is reactance control mode. In voltage control mode, the voltage injected by the compensator is independent of the line current, no matter what is the line current, but obviously there that will be restricted by the rating, okay, by the specifications, or by the safe operating zone area. But during this operating region, the voltage is maintained constant, whatever be the line current. And for reactance control mode, a, a particular reactance is maintained. That's why the voltage and current there, they linearly vary. There is a linear relationship. As the current varies, the voltage varies linearly. Okay. So these are the two control characteristics. Yeah. So SSSC has many advantages over the other series compensator that we saw, the TCSC, right? Because there is no bulky capacitor or inductor that is required, and and there is and it can provide both active and reactive power. That is true. So SSSC is advantageous in many aspects. Right. So if you do not have any question, then the session, we can conclude this session. I hope uh, you could understand the concepts and properly, and you got to learn something from these sessions. You got some uh, in terms of the assignments or problem solving, you got some idea after attending these sessions. Thank you for attending. And okay, so yeah.